Okay, so good afternoon, all of you.
Good afternoon, sir.
Okay, so let me start today's lecture. In fact, I will try to finish off your course today itself. Okay, just a minute. Okay, so in the last class we were talking about different types of systems, communication systems, and we have talked about the radio receiver, radio transmitter. Then we have talked about the mobile communication system and satellite communication system. And we mentioned about the different types of signals that we communicate. And we said that in the 19th century, people were mostly communicating voice and messages in telegraphic system and voice in telephonic system. So that was the main signals, main type of signals which were communicated in 19th century. But in the third decade of the 20th century, this television that came into existence, and from that time onwards, this video signal, the picture video, that also was started being communicated over the communication channel. So that was also one part of the communication that became a part of the communication signal, this video and images. Okay. So television system is also a very important communication system, and that is also used and is still there. And in fact, nowadays that has become one of the most important communication system. You know, not only in television, now we have video conferencing, video phone, all these things. Okay, although the television system has now changed, it is mostly it is nowadays digital television. When we talk about video phone, when we talk about video conferencing, it is digital television, digitized. Okay. However, we will now study a bit about the original, means the previous television system, the analog television system. Because digital television system has actually evolved from this analog television system. So first, let us see that how the picture or how a outside world video scene is converted to electrical signal in a television system. So here it is the diagram, the schematic diagram of a television camera. Okay. So this is the outside world video scene, and you have some lens, focusing lens, through which the outside world light will be falling on a photoconductive surface inside the camera. There is the video camera. Okay, you have a photoconductive surface. The schematic diagram is something like this, that you have a cathode from where you have an electron gun falling on this photoconductive surface. And this photoconductive surface is connected to the ground through a resistor, and there is a power supply. Okay. The video signal is generated and it is taken out as the output from this point. Okay. So what happens that this photoconductive, I have shown here, the photoconductive coating, the photoconductive plate which is there, it's like this, that you have a glass plate. On the glass plate you have a conductive coating on the glass plate. Okay. So this is the conductive coating on the glass plate. Now this conductive coating on the glass plate is something like this, that depending on the light falling on that conductive coating, the resistance of that conductive coating, or you can say the conductance of that conductive coating, will change. If more light falls, then it becomes more conductive, that means the resistance decreases. The resistance R decreases with light. When more light falls, the resistance R will be small. Okay, sorry. The resistance R will be smaller for more light. Okay, so it's like that. Now you have an electron gun from where the electron beam is falling on this. Okay, so this makes a complete circuit. You can see from here that from this ground you have the power supply, then RL, then through this photoconductive surface, through this photoconductive coating, okay, you have, and through this electron beam you have the complete circuit made. So basically the electron is flowing from the ground through the electron beam, through the RL, and then to the power supply. Okay, so electron is flowing in this direction. That means current I will be flowing in this direction. Current I is flowing in the opposite direction. Okay, so when this electron beam is falling at this particular point on this photoconductive surface, then basically the circuit is made from here. The circuit goes like this, and through that particular some R, it's continuous. I have schematically I have drawn it like this, that you have R like this, but actually it is a continuous case. But at that point where it strikes, the electron beam strikes, the R connecting this, the R at that point. So it is basically the path through this. Okay, the path through this. So that one offers some resistance. At that point where the electron gun is striking, at that point the path will be offering some resistance. The path through the photoconductive coating will offer some resistance, and then the circuit is complete. It's like this. Okay. So accordingly,
Generated.
bolo.
Sir, how we can then get the signal, because if there are different resistance, then how we can measure that from which part there was different?
Other resistances are something like they are disconnected now. They are just hanging. So it is only as if there is a resistance in this part which is connected. The others are hanging. Okay.
No, sir, I am asking that how are we measuring the coordinate of that resistor, because then only the signal will be processed.
We are not going to measure the coordinate and all these things. It will be continuously, it will be accordingly the video signal will be generated. Okay. Now this electron gun will be continuously scanning this is a square, somewhat like a square photon surface. Okay. What it will do is that the electron beam, it is written here, an electron beam scans the photoplate. The photoplate will be scanned, okay, bottom up, from the bottom to up. It will continuously keep on scanning, and right to left order. Why? Because this image actually will be formed inverted. Okay, the image will be formed inverted. So basically, if I want to scan this outside world image from top to bottom and from left to right, but that image will be inverted here. So I will be doing the scanning in a bottom up and right left order. So the outside world seen in the form of light is falling on it. And when I am scanning it, so basically that electron beam will be continuously scanning this outside world, whatever the brightness of that outside world is. So accordingly some light is falling on it. So this electron gun will be scanning. So basically it is scanning the outside world image in this order, from top to bottom, from left to right. But since the image is inverted, it will be scanning in here inside, it is scanning in this order, bottom up, right, left. Okay. And at some time, at some instant of time, the electron gun is falling at this point. Okay, that means it is basically measuring it is essentially measuring the brightness at that point. Okay, the outside world image, outside world scene, whatever the scene is there, whatever the light is coming from that point at this position, that brightness of that light is essentially getting measured. Okay, it is essentially getting measured. How? Because this V video, this signal, will be equal to V supply, the supply current, minus I into this RL. That will be the current. That will be the voltage produced here. Okay, that is what I will be taking out as my output signal. Now this I will be more. Okay, so when it is more bright outside, the corresponding R at that point, the corresponding R at this point will be less, and hence this I will be more, and hence this your V video will be less. Okay, you just see the relation. Okay, or you can say V video will be equal to this. You can check it. You can calculate it, and you will see that. See, this is it's a means I have given a simple relation, although it's not so simple, but it is just for your understanding that how actually the video signal is produced. I have given a simple modeling of the things. Okay, the circuit is not so simple, but I am just giving you a simple circuit modeling so that you understand it easily. Okay, so it is more or less something like this. It is happening more or less something. It is happening like this, but it is not actually so. It is not that R is exactly so. Okay, it is just a simple modeling. I am doing it for your understanding that depending on your brightness of the light falling at different position, the resistance R will be different at different positions. Okay, so it is as if there are different resistances R like this, as if. Okay, it is not so simple, but more or less you can model it like this, and hence you can see that your V video will be equal to V supply into R by RL plus R. You can do, if you do a simple modeling of the circuit, it will come out to be like this. Okay, you can check that. Now this electron gun, how it is scanning, obviously this you will be having something to change the direction of the electron gun. You have two horizontal magnetic deflection plates. Okay, so magnetic field will be changed here in this deflection plates, and because of the change in the magnetic field, you know, when magnetic field changes, the electron will also change in a magnetic field. Okay, so the direction of the electron beam is changed by changing the magnetic field here in these two horizontal plates. So accordingly, the electron gun can move up and down. Okay, by changing the magnetic field in these two horizontal plates. And there is also a pair of vertical plates. I have shown it here dotted. Okay, so there is a pair of vertical plates, and by changing the magnetic field in that vertical plates, you can have the right left movement of the electron gun. So basically the electron gun will be now, you keep on changing the beam, the direction of that electron beam. Okay, and at any point of time where the electron beam is falling, depending on the resistance of that point, resistance of the this conductive coating at that point, and that resistance depends on the light, amount of light falling at that point, you have your V video will be equal to this. This is how you will be getting the relation. So this is what we are getting. So it is a simple modeling we are doing. It is, although it is not so simple thing, it is not exactly R and all these things, but more or less you can see that the video signal that you will be getting will be inversely proportional to the brightness of the projected scene, because V video you are seeing that it is directly proportional to your R. Okay, because when RL is very large compared to this R, then it becomes more or less V supply into R by RL. Okay, this R can be neglected in the denominator, it can be neglected compared to RL, So you see your V video is proportional to R, and since R is inversely proportional to brightness, you get your V video inversely proportional to the brightness of the light falling at that point. So depending on your scene falling on this uh, photoconductive surface, you get your V video. So it will be like this, that the scan, it keeps on scanning from scanning this outside wall image, which is inverted here, inverted one. You keep on scanning in this order, keep on scanning in this order, and you get your proportionate video signal depending on the brightness of the outside world scene. Okay, so that is how the video signal you are getting, and then we are receiving that, say, at the TV set at your home will be receiving that signal, and now it has to reproduce that scene on the picture tube. This is the picture tube. Here again you have one cathode which is generating a electron beam, and that electron beam will be projected. It will be striking the screen here, the picture tube screen here, which is coated with phosphor material. So wherever the electron beam is striking, the phosphor material will get illuminated, and the amount of illumination, the brightness of illumination will depend on how many or what is the intensity of this electron beam. If more electrons are striking the phosphor screen, then it will be more bright. It's like this. Okay. Again, here we have this vertical deflection plates and the horizontal deflection plates, which will be now regulating the movement of the electron beam. And here the electron of the direction of movement of this electron beam will be from top to bottom and from left to right, because here now I want the scene to be produced in this proper proper way. There it was inverted, but here I want it to be in the proper proper way. So that's why that's electron beam will be moving in this direction. Okay. Now, how we are controlling the brightness? Because I want this brightness should be such that whatever the brightness was captured there, okay, so it should be proportional to that brightness, the brightness of the scene produced here. So that means the amount of electron or the intensity of this electron beam has to be proportional to the brightness of the scene that I have captured here. Okay. So according, now here I have a grid. Okay. There are other grids for focusing and controlling other things. So forget about all those things. Just there is a grid just in front of this cathode. These grids are all, this grid and all this focusing anode and all these are all positively, you apply positive voltage to them. So depending on the positive voltage that you are giving them, the electrons will be, if you are making them more positive, more electrons will be coming. If you are making them more negative, more electrons will be actually, they will be retarded back. They will be reflected back, because if you make them negative, they will be reflected back. So you can understand that this anode, if I make them more and more positive, then it will from this electron beam, it will take more and more, it will pull more and more electrons from this electron beam, which will be going to the phosphor state. Okay, so that is how it happens. So now here I have a grid, and this grid actually controls the brightness. Okay, this is the grid where I will be applying the control signal. Okay, the control signal. And this control signal, you can see I have given the basic, again here it is just a basic relation I have given for your easy understanding, although the circuit is not so easy, but I have given a simple circuit here for your understanding. If you have your V video, the signal that you have which you have received if you apply it to this transistor amplifier, then you see your output V control that you take from here. Okay, that V control will be equal to VCC minus ICRC. IC is equal to beta into IB. You know all these things. VCC, so it becomes VCC minus beta IB RC. Again, this IB will be proportional to the video voltage that you apply here. So I can write it as VCC minus some constant KV video RC. Okay, beta IB, IB is proportional to V video. So I write it as K into V video RC. I can write it like this. Now this V video signal, I am just showing it. You can check that if I now replace V video, now it becomes V video is what? If you see here, V video was V supply minus IRL. Okay. Now if this V supply is more or less equal to this VCC, then you see that they cancel out and all these things will happen, and you get your this V control will be equal to IRL. You can make it like that by adjusting your K, by adjusting your VCC, by adjusting your V supply. You can make your V control is equal to IRL. Okay, just check it, because here you can see that V video is equal to something minus some constant minus IRL, and here you are having VCC minus V video into some constant. So it's like that, V control. So I can make this V control equal to IRL. Okay, I can make it like that, or it may be some constant into IRL. So anyway, V control you can make it proportional to IRL. Okay, RL is constant according to my modeling. RL is constant. So V control is basically now proportional, is equal to is proportional to your I, and this I, current I, as we have already seen, it is also proportional to the brightness. More bright, more current. So ultimately I have this V control signal is proportional to the brightness of the scene. Okay, and that V control is applied in this grid. So if you have more brightness, this anode, the grid anode, will be having more positive voltage, and hence it will pull more electrons from the cathode, and hence you will be having more brightness. So it is more or less, this is the working of the TV system, that the video scene is captured by your camera, and then it is displayed in your TV strip, that picture tube at your home. It's not your LED or the LCD TV nowadays you are having. Okay, so it is the old days television which still you are having. Many of you are might be having at your home. So it is that TV only. Okay. Now coming to that, how we are actually getting this moving picture. Okay, this moving, you see a video, a moving picture, how it is actually generated. Now going back to the old days motion picture movies, that still you go to the cinema hall and you see movies, but anyway nowadays movies are projected through digital system. Okay, through digital system, digital projectors. But in earlier days, you know, it used to be some projectors through which you used to project. We know that the persistence of vision is 1/16th of a second. That means if I show you something, it remains in your brain for 1/16th of a second. So that much time it will be there in your brain. Okay. So if I show you another snapshot, okay, I show you a snapshot of a video scene, and then within 1/16th of a second, if I show you another snapshot of the same scene, then you will feel that it is there is a continuity. Although I am showing you the snapshots in two different times, snapshots of two different times, but since I am showing you within that 1/16th of a second, so you will not be able to make out that there was something missing in between. You will see it as if it is a continuous picture, because you are still having the previous scene in your brain, and the next snapshot which I am showing, it will be a continuity, it will be in continuity to that whatever it is already there in your brain. So that is basically the idea of making a moving picture. So in earlier days in the movie theater, this is how the movies used to be done, that there used to be 24 frames of a moving scene projected. See, minimum 16 required, but for better viewing, 24 frames used to be projected. Okay, it is like this, that the reel used to be there, the some movie all this film used to be there, that film used to pass before a light. Okay, through this thing, so it used to this machine, there used to be all this projector used to pull this film, bring the film in front of this light. Okay, and there is a shutter, that shutter will open for some time, this will get projected here, then the shutter will close, and when the shutter is closed, then this spool here will pull the film to the next scene. It's like this. However, there is some problem. There was a problem that in between two scenes, since there is some blanking period when you are closing the shutter, pulling the frame to the next scene, so there was some blanking, and that blanking will be used to create some flickering disturbance. Some flickering used to be there, that something is flickering there. So like that, that problem was there. So in order to reduce that, people, what they did, they increased the number of frames. Then they increased the number of frames to 72. Actually, it is not increasing the number of frames, but what they used to do is that the same scene, they will be showing it 3 times. Okay, so ultimately it used to become like 72 frames. There will be blanking between 72 frames. This blanking was made very fast. Okay, the blanking, in between blanking was made, in between this blanks in between the frames was made more. Okay, it was more of it. Now this is something like, if you look into your ceiling through with your fan on, the fan is rotating. If you see, if the fan is rotating, the fan is like the shutter. The fan is like the shutter, which is obstructing your view for some time. Now, if the fan is rotating at a slower speed, you will see that you will be able to make out that something is obstructing your view for some time. The blades of the fan is obstructing your view. You will be able to make it out. But if you increase the speed of the fan, you will see that the blades are now more invisible. It's like more invisible. You will be not able to see the blades. Okay, you will be able to see the ceiling better. Okay, so that is something what actually people did here. By increasing the shutter speed, the shutter is to move 3 times more frequently. Okay, and because of that, the blanks are coming more frequently, just like the fan speed. Okay, and that flickering is now reduced. Okay, so all this actually depending on how our brain can perceive the things. Based on that, people made all these developments. Now in television, we are using basically the same idea. So here, instead of 24 frames in our television system, the television system in our country, which is called the PAL system, and many other countries are use PAL system. So in television, in our television system, we use 25 frames in a second. And here, as in the movie theater, they used to split 24 to 72. Here we are not doing that. We are actually doing 25 frames split into 2 fields per frame. So we are finally having 50 fields per second. So there will be blanking in between the fields. Okay, again for the same reason. Okay, so ultimately it becomes 50 fields per second, and these fields are interlaced fields. I will show you that what is interlaced fields. 2 fields are interlaced together to form 1 frame. Okay, now the reason for taking 25 frames or 50 fields 25 into 2 bits, so 50 fields, is because of our power line frequency. You know our power line frequency, the electricity that comes to your house is 50 hertz. Okay, so using this 50 frames, 50 fields, or we can have our things, means the television system at our home. If the oscillator is not running properly in your television system, that can still correct its oscillation frequency by adjusting it to the power line. So it was because of that only people selected this 25 frames. Another system is there, SECAM system, SECAM, ACCAM, SECAM system is also used in some countries. It is more or less like the pulse system. But NTSC system, the National Television Standard Committee, they developed in USA, they developed a system, NTSC system, which is used in some countries, the countries where the frequency, power line frequency is 60 hertz. You know, in some countries they have 60 hertz power line frequency. They use this NTSC, where they have 30 frames per second, that means 60 fields per second. Okay. So this is basically what is happening in our television scanning, okay, and how the fields are produced. One frame time you can calculate, since I have 25 frames, one frame time is 0.04 second. Now in our, what I am discussing here is with respect to our system, our pulse system. In our pulse system, we have 625 lines. We have 625 lines per second. So you can calculate again that if one frame time is 0.04, then 625 lines per frame means one line will take time 64 microseconds for scanning. So one line is basically from one side of the one, from left to right. However, the 64 microsecond is actually divided into two portions. For 52 microsecond, you have the visible line scanning from left to right. Okay, left to right. So this is the 52 microsecond. I have this signal applied to the vertical plate, vertical deflection plate of the picture tube, or in the camera. Camera is also synchronized in the same way. So this is the signal, sawtooth wave type signal applied to your vertical plate. So for 52 microsecond, when the magnetic field is increasing in one direction, then the line will be traced from one end to the other end. Okay, the deflection of the electron beam will be from left to right like this for 52 microseconds. Then for the next 12 microseconds, you have to allow that time for this scan to retrace back. So 12 microseconds, during that time you do the blanking. There will be no picking up of the signal. The signal will be blanked. Okay, because that time we have the horizontal retrace. Okay, so that is how every line is, you do the raster. This is called raster scanning. Raster scanning, another one is random scanning. But here, since it is in a proper sequence, we call it raster scanning. So this raster scanning is done in this way. For 52 microseconds, you go from left to right, and then in 12 microseconds, you do the blanking. So that is what I have shown here dotted. That time the deflection plate will be having the signal falling down. So the deflection plate will have the signal applied sawtooth wave falling down. So that it will retrace back in the from right to left, and that time it will be blank. Okay. Now this whole frame, as I said, it is divided into two fields. Okay. Since I have 625 lines, in each field I will be having 312.5 lines. This is very important. Why 0.5? That's why I have taken it here odd number. If it is an even number, then it will be not 0.5. But this 0.5 is very important. What happens when I am having the odd numbered field? The first field is the odd numbered field. Second field is the even numbered field. When I am having the odd numbered field, you can see here, I am tracing like this. I am tracing like this, and finally I come to 312.5 at the middle of this. At the middle of this point. So it is actually not 312.5, it is actually 292.5 visible lines will be traced like this. This is the 292.5. 292 is completed here, and then 0.5 line here, half the line, and it stops here. It comes up to this point. And this then for 20 blank lines period, 20 lines period, that means one line period is 64 microsecond. So 64 microsecond into 20, that is 0.00128 second. You will go blank. That time you have to go back on top. Okay, go back on top. Again, I am showing it here. This is the signal that will be applied to your horizontal plate for vertical deflection. So this will be the tracing will take place. So the scan beam will be going in the horizontal direction, and at the same time will be moving slowly in the vertical direction, and it will come here. And then when it comes here, then for 20 this 0.00128 second, that is for 20 line duration, it will go blank and it will fly back to the top. Now you see, since it has come here in the middle, it will fly back. 20 lines it will trace, although I have shown here only 2 lines just for here, but actually it will go like this, 20 lines, because 20 lines it will be, the horizontal deflection is still there. So during that time it will go back and it will come here, it will reach here, because it has stopped in the middle, so it will come in the middle. And so when I do the next field tracing, you see this tracing will be exactly in between. In between. If it had come here, then it would have overlapped on the previous scan position. But since it has come in the middle, it will be now scanning exactly in between the 2 lines, earlier scanned lines. So these black lines you can see, these black lines were the scan lines in the first field, and this blue line in between is the scan line in the event field, the second field. Okay, so that is why actually it is required that 0.5, if it comes to 0.5, then it will go back here, and then the next field scanning will be exactly in between the lines of the previous field. This is called interlacing. This is the interlacing of the scan lines. So that's why we call it interlaced fields. The fields are interlaced. Okay. So this is how the things work actually. Okay, this is how the things work. So this is just a basic idea about the things working. Now coming to the color TV, you know that we are mostly, we have color TV. So basically again the idea that how the color is produced. Now this color actually is not produced, this color is not yet, means you cannot generate a color, okay, because you know defined colors means different frequencies, different wavelengths. Now in the last class someone asked me that whether electromagnetic waves having different frequencies, whether they will be mixing up, whether they will interfere with each other, and I said no. Different frequencies, they will not, means one signal, one sinusoid of one frequency and another sinusoid of another frequency, they will remain as they are. It will be sine theta 1 plus sine theta 2, but it cannot produce a new frequency. They will not interfere and they cannot produce a new frequency. And that is what actually one good example is in this light. Light is also electromagnetic wave, okay? And you know this white light that you are seeing, this actually white light is an impression, okay? White light is actually composed of all different wavelengths, When they are coming, it looks like as if they have mixed up, okay? But actually not. All the different colors, they retain their frequency. That you can always split it out, isn't it? Using a prism, you can split all the light again. Okay, all the different frequencies can be split up. So that means basically, that is what I said in the last class, that they will be there. All the different frequencies will be there in the, but they will not intermingle with each other and produce another frequency. They will not do that. You can always split them out. You can always separate them out, the different frequencies. That is what we do in light also. The white light is composed of all different frequencies, but you can always separate out a particular frequency from the light. Okay, that is what any electromagnetic wave we can do it. So here also, the idea is now I suppose I want to have a particular light of frequency 500. Okay, but I cannot produce it on my own. What we do is that we try to produce a sensation of that particular color. Okay, the sensation, how it is created, that we have in our retina 3 different types of cone cells, and these cone cells, they respond differently. These 3 different types of cone cells, they respond differently like this. One type of cone cell respond more to the red color. One type of cone cell will respond more to the green color, and one type of cone cell respond more to the blue color. Okay. Now suppose a light falls on my eye, okay, which is somewhere around this 500 nanometer wavelength. Okay, this is the light falling on my eyes. Now when this light falls on my eyes, these 3 different types of cone cells will have 3 different sensations. Okay, the amount of sensation that will be produced, okay, the response that will be produced in these 3 different types of cells, it will be defined. So you can see that green, for this particular light, the green I am writing it, suppose it is xg is the amount of response, xb is the amount of response to my blue colored cone cells, and xr is the response to the red colored cone cells. So these 3 different types of cone cells will be responding in 3 different proportions. XR is to XG is to XB. And the relative proportion of these 3 responses, that gives me the sensation of the color. The brain is able to do that. Okay, brain makes out the color like that. That how the different cone cells are responding. So if a blue light is falling in my eye, or say ultraviolet, a violet light is falling in my eye, then in that case, this XR will be almost 0, XG will be almost 0, XB will be very high. So when I have my cone cells, blue cone cells are responding much more than the XR, than the red and green, then I know that this is okay, this is a blue color, like that. The sensation comes in the color sensation comes like that. Okay. So we want to produce the same sensation in order to make a color. Actually, the color is not produced. I cannot make a signal of this frequency. What I do, in my eye, I will be projecting some blue light, some red light, and some green light, and I will make these 3 types of cone cells, make them respond in the same proportion. I will make them respond in the same proportion. That is what I will try to do. And by doing that, we actually create a sensation. We create the sensation of this color. We cannot produce a new color. We cannot produce a new frequency from other colors. Okay. So that is how the color, and you know that you must have observed everywhere it is written red, green, blue. Even in your television system, you can change the reddish, that you can change the greenish, or you can change the bluish thing. Okay, you can change it. So basically it is red, green, blue in 3 different proportions are projected, and that when reaches my eyes, they are coming into my eyes in such a proportion that it creates the sensation of a color. Okay. So accordingly, the color TV camera is like this, that the light coming from here, you first filter out a portion which is near the blue, you filter out a portion which is near the red, okay, and you allow the green portion to pass through. So the red portion is taken out, okay. So some light from here, the portion which is in that range of the frequencies, they are taken out, and it is redirected here, and then it is filtered here and goes to one camera. Then another portion will be redirected here. So you use some dichroic mirror for filtering out a portion of the blue wavelengths from the light, and you redirect it to another camera, and rest of the light will be going to the green camera. So the all the light falling on in my camera is now divided into three bands, more or less 3 bands. Okay. The response of this, actually why we are doing this, the response is somewhat, we try to make it in such a way that this thing is the response is somewhat like the response here, what our human eyes is having. More or less, this filter here, the color filters here, in the last class I have shown some picture of the filters. Okay. So the filters are more or less will give you the response somewhat like this. They will be having something like this, the response of the filters. So the red filter, so you first filter out the red portion of the light, and then when you pass it through the red filter, then you will be having somewhat the response of the light will be like this. Okay. So like this, more or less whatever, when the light falls in my eye, then my cone cells will be responding. We want to make somewhat like that. It will be not exact. Okay, it will be not exact, but somewhat like that. We want to create the responses at the output of these 3 filters. The 3 responses we want to create. So it is basically the optical modeling, you can say, optical modeling of our retina. We are doing it. And then the light goes to the 3 cameras, and these 3 cameras will be just in the same way. Once we have split the light into 3 portions, then this light will be now producing the 3 different. Now here we will be having 3 signals, not 1 signal. The earlier one was monochrome, black and white TV, so it was only based on the brightness. But now here it is color TV, so I will be having R, G and B. 3 signals I will be having, which will be going from the camera, and this will be actually now transmitted. But actually we don't transmit R, G and B signal. What we do, we transmit a signal in this form, composite signal, where we say Y is equal to 0.3 R plus 0.59 G plus 0.11 B. So the 3 signals are multiplied in a certain proportion and then added up. This Y signal corresponds to the brightness or the monochrome signal, the black and white signal. Okay, and then I use U, I use V like this. This is the U. So these 3 signals, instead of RGB, we transmit YUV. Again, it is our pulse system. In our pulse system, we transmit YUV. Now you can see that there is a relation that at the receiver, if I receive YUV, then I can always get back my RGB from here. So basically that is what is transmitted, YUV transmitted, and then at the receiver, I get back my from the YUV, I get back my RGB signal. Okay, and then this RGB signal is put into the electron, again this picture tube. In the picture tube, now here I will be having 3 electron guns. 3 electron guns will be falling at 3 different closely spaced 3 different types of phosphorus. Okay, one beam will be falling here, one beam will be falling here, one beam will be falling here. You use one shadow mask so that all the beams are concentrated at one point in these 3 positions. These 3 points, these 3 are 3 different types of phosphor dots. They are phosphor dots, 3 dots of phosphor. But the phosphor material is different. The electron, when it falls here, the electron beam from here, it falls at this position and it gives you a red light. So this red light here will be proportional to the red signal. The electron beam falling here will be proportional to the blue. Okay, that will be to the blue signal, and so it will emit this phosphor material is different, it will emit a blue light of proportional to the blue signal, and similarly I get a green signal. Now these dots are closely spaced. They are all, you cannot make out these dots. I have shown it here in a big way, but actually on the TV screen, they are very close. So when you look into at this position, when you look into it, you cannot make out these three dots separately. You see as if they are mixed up, and you see the sensation of the color that is produced in your brain due to these three different lights, RGB. This is how the color sensation is created. You don't create the actual color, but the sensation is created. Now one question comes that if I am ultimately using RGB here again for this electron beam to be modulated, then why I am unnecessarily sending this YUV? Because you have to then do extra conversion at the transmitter and extra conversion at the receiver. The reason is that before the color television came into being, before it was invented, this color television, monochrome TV was there. So all around the world, people who were having television, they were at their home, they were having black and white monochrome TV. And that black and white monochrome TV was capable of receiving black and white signal, okay, and then displaying the picture in black and white, having only one electron beam in their picture tube, okay. So that picture tube requires black and white brightness signal for showing you the black and white picture, okay. Now when color TV came, then the government of all countries, they said, okay, now from today we will be starting broadcasting the color TV signal. Now if they have transmitted RGB, now what will happen to the black and white TVs? They will receive either R or either G or either B. They cannot receive all three because the television set is for only one signal, okay. So if they receive only R, then they cannot see the picture properly. They will be actually seeing only how the red signal is changing, how the red component of the signal is changing. They will see that scene like that. So they need that brightness signal. They need that brightness signal. So government decided that time for all over the world, it was decided that instead of transmitting RGB, we will convert the RGB to YUV and transmit it so that it is still compatible to the black and white TV. So black and white TV users, they will be receiving only the Y signal and they will be running their TV set. Their TV set will be running fine. Whereas a person who is buying a color TV can now, because this color TV set is now new, so that TV set has been now built up, because you cannot change the monochrome TV set, because then you have to spend money. Every person has to spend money to change the TV set. That you cannot make any change in that already existing set. So whereas you can make a new television set, color television set, where you can reconvert YUV to RGB, you can make it that provision there. So that was the idea, and that's why this YUV signal was made. Now if you see this why we are taking this particular weightage? Why not exactly 1/3, 1/3, 1/3? The reason is that again, our human sensation is like that if you look into some green light, that green light is much more brighter compared to red. Okay, if you see three balls, one green ball, one red ball, one blue ball, you will see that the green will be looking more bright, red ball will be looking a bit dull compared to the green. Blue, generally it will be very dull. It will be not that bright. And that's why this relative brightness weightage has been taken for RGB to produce the brightness signal Y. Okay. So that's more or less about the television system, and this is the television broadcasting spectrum, the wavelengths, that frequency ranges that are used by the television set. This is the luminance. This is the, as I said in the last class, that vestigial sideband is used. Hello. vestigial sideband. Okay, this is the vestigial sideband is there, 1.25 megahertz vestigial sideband is there. Okay, and this is the actual luminance Y signal is transmitted here. UV, they are transmitted in a form of quadrature amplitude modulator. Actually, what we do that U and V, these two signals, we make it as if they are like a complex signal. You know, X and Y, X plus IY or JY. We make it like a complex signal. So similarly here, U and V are made like that. One is taken to be in the quadrature of the other. So that's why it is called quadrature amplitude modulation. That is, I have not discussed that particular method of amplitude modulation, but it can be done. Two signals can be combined together, okay, in a quadrature form. And basically for one signal you use cos 2 pi fct as the carrier. For the other one you use use sin 2 pi fct as the carrier. That is what I actually use. So UV signal are placed here. Now the question comes that are they overlapping? It's not so, because this chrominance, this Y signal, if you look more closely, I have given a more closer look of this. The spectrum is like this. There are some gaps in between. It is something like this. It will be something like this. That is because of the lines and all these things. You have frame rate, you have line rate, all these things. Because of that, you have something like this. It becomes a bit discrete. The spectrum is not so continuous. It is a bit discrete with some gaps in between. The UV signal, the UV spectrum is actually placed in between. Okay, it is interlinked at this position. In this position, wherever the gaps are there, in these gaps, the UV signal is also like this discrete. So they are put in between the gaps. Okay, so that you utilize it. You don't use extra bandwidth for this. Now this chroma, this is called the chroma signal. Any color is having three attributes: brightness, hue, and saturation. Brightness is here Y signal. So hue and saturation, that information is carried by U and V. Okay. So and as I said last class that the audio signal in television is frequency modulated, and this is placed here. Okay. So total bandwidth required is actually 8 megahertz, including a guard band 250 kilohertz. This guard band is that so that the next TV channel starts with a gap of 250 kilohertz in between, so that there is no overlap. So this is more or less the television system spectrum. Okay. So today I have completed up to this. Okay. So in that I couldn't complete few slides left out, some 5-6 slides just on the digital communication. Just I'll be giving you a basic idea of the digital communication. So since I couldn't complete it, Friday I will be first completing this within some say first half an hour or so, and then we will start the quiz. Okay, the quiz will be for the 30 minutes. So I will be completing this part in the first 30 minutes, and then in the next 30 minutes we will be having the quiz. Okay, so your quiz syllabus is up to today. Whatever I am teaching you up to this is your quiz syllabus. This digital portion, few slides which are left out will be in your end term, not in your quiz. Okay. I will send you the instruction about the quiz in the MS Team. I will send the instruction before. I have already posted this lecture notes. You go through the lecture notes. Okay. You have 3-4 days time to go through the lecture notes. Okay. Okay. हाँ बोलो. हाँ.
Television system when scanning was when in television system scanning was done, first it was done bottom top and then top bottom. Can it be done quicker?
I'm not getting you. Actually your voice is not coming clearly. You are saying about the scanning.
Yes, sir. So first it was bottom top and then top bottom. So can it be done vice versa?
Why? Why we are doing that? Means you are asking why we are doing that.
Yes, sir. Sir, like, can we change the order?
Why? See, in the camera, the outside world picture actually will fall on your camera's that plate, na? It will be coming falling in an inverted manner. You know that through the lens when it comes, na, the picture always gets inverted, na? So actual real world is somewhere. Okay, just a minute, and I'll be sharing that picture. I think this one. Huh. See here. Say, suppose this is my outside world, okay? And when I want to reproduce this picture, when I want to reproduce this picture on the screen, I will be reproducing it exactly in this way. Okay, in this, this will be the actual position of the picture on the screen. Okay, but this picture actually is falling on the screen. This point, this top left will be coming as your bottom right, isn't it? It gets inverted. It is getting inverted. You can see here, this point will be coming down, this point will be coming going up. So this point is coming here. Okay, so I have to, when I do the scanning, I start my scanning from bottom only. From, if I want to find out the brightness at this point, then I have to basically do the scanning at the bottom right. Although here it is top left, but I have to do the scanning here at bottom right. So when I'm doing the scanning from, if I want to do the scanning in this manner, that left to right and then top to bottom, here I have to do the scanning just in the opposite way, isn't it? Because the huh?
Right.
Huh? Your voice is
In the
breaking.
next slide,
Next class you will be asking. I'm not getting your voice is cracking actually.
Sir, now am I audible?
Yeah, now you are audible. Yeah.
Sir, in the next slide, it is given that it is from top to bottom.
Because there it will be, here the scene is created, na? Here the scene is created, actual scene is created.
Yes,
So
sir.
I want that top left to be created here. Top left will be created here on top. Because this is what I will be seeing. Now I will be sitting here and looking into the picture tube. So I will be seeing that picture. So here it will be in the proper orientation. If the orientation is, should be the top will be on top here. But when I'm doing the scanning, this top actually is coming here. So scanning has to be in the picture tube. It has, in the camera, it has to be done in the opposite way. Okay.
If we do it vice versa in the camera, like it is from top to bottom, and in the picture,
You can do it. Okay, you want, means here you do it from top to bottom, but there you do it from bottom to that. You can do it, but anyway, this is what people have made it as a convention. Something has to be fixed, right? Someone has, because all the industry people, they have to make a they have to fix up a standard. Otherwise, what will happen, that the TV broadcasting station is using some camera with a certain standard, and your receiver is doing you have purchased your receiver TV set from some other company which is doing in the other way. So that should not happen. So that has been actually fixed up by the people in the whole world. Some standard committee is there. They have fixed it up that we should do it in this way. That in the camera we will go like this, in the picture tube we will go in the other way. Okay, that has been fixed. Otherwise, here also you could have done this way, that I will go from top to bottom here, and there I will go from bottom to top. Okay, but it has been yes, specified because so that all TV sets all over the world, they are compatible to all the television stations. Otherwise, my TV set, suppose it is compatible to India, but I cannot use it in some other country. So all the countries, they have to standardize all the cameras, So they will be doing it, all the cameras which are taking the picture in their TV studio. They will be taking the picture in this way, and all the television sets will be reproducing the picture in that way. So that has been standardized. Okay,
So, thank you, sir.
clear? Okay. Okay, so you may leave. Okay, so Friday we'll meet.